Morning, guys. Looks like we lost a few of you between yesterday and today. If you can give me a green check mark, let me know you're with me, and we'll get going. As well, if anybody had any questions from, I guess we finished up Unit 5, is that right? Yeah, Unit 5 from last class. Anything in the learning guide that you ran into issues with, you want to throw those in chat, I'd be happy to go through those. If not, we'll just mosey on into Unit 7. I know we've been seems like we've been going through a ton of units really quickly, but I mean, Unit 5 is just so short. As well, Unit 6 didn't have a ton of material in it either, so those kind of two went by really fast just because there wasn't really that much there. Unit 7 we'll spend a little bit more time on. And then once we're done Unit 7, that although it isn't technically chemistry, Unit 7 looks a lot like chemistry. And there'll be a module exam, so all of the chemistry stuff together. So Units 4, 5, 6, and 7, there'll be a test on all that stuff together. Kind of like what we did at the end of the biology unit. When's Unit 5 due? You should have probably been done it last day or yesterday. I'd love it if you had it submitted by tomorrow, would be great in a perfect world. So tomorrow would be good. I just don't want Unit 5 to lead into Unit 7 to lead into the next one, and then you just kind of run out of time down the road. So yeah, we'll stick with Friday. I think that's pretty reasonable. If you have issues, let me know. But we'll just go with that. Cool. Nobody had any questions from Unit 5? If something does come up, let me know. But if not, we'll jump right into radiation, radioactivity. I really like this unit. Some really, really cool stuff comes out of it. It's kind of a newer science. And yeah, it's some interesting stuff here. Do you mean the learning guide or the test? Yeah, if you can get the learning guide done on Friday, that'd be fine. And if you get the test done by the end of the day on Monday, that would be good. So learning guide Friday, test done by the end of the Monday. That'll give you Friday, Saturday, Sunday, Monday, lots of time to do that test. All right, so radiation. Right now, you are constantly being bombarded with radiation, and it comes from everywhere. And there's something called the natural background radiation. That's just the radiation around us all over the place. So a lot of people hear the word radiation and they think like, oh, nuclear bombs and deadly and you're going to die. You don't want to get radiated. It's just going to be bad stuff. Well, there's harmful radiation and then there's radiation that's not harmful. Things like light. There's lights in front of me. They're bouncing light off me. It's going to the camera. Your screen that you're looking at, it's emitting light. It's hitting you. That's radiation. If you were to turn on a radio in your house right now, or you went out to your garage and carport, turn the radio on in the car, it would pick up a radio station. That's radiation. Put some food in your microwave, heats it up, microwave, that's some radiation. Go to the dentist, get an x-ray on your teeth, radiation. So you can see beside me here, you have different types of radiation. Waves that are really, really long are things like radio waves, and then you get a little bit shorter waves or microwaves, infrared, visible, and then ultraviolet, X-rays, and gamma rays are kind of the most energetic rays that there are. So this is called the electromagnetic spectrum. It starts with really low energy stuff on the far side, and then as you move across, it gets to higher energy stuff. So the more energy the radiation possesses, the more dangerous it is for humans. And I'll give you an example of where the electromagnetic spectrum kind of gets dangerous for us. So if you've ever sat outside, go to the beach on a sunny day, you sit down on the beach, you feel warm. What type of radiation makes you feel warm? Some people may even have these in your bathroom. I know it was really common in like the 70s to put a special type of lamp in your bathroom. It's kind of like reddish. Maybe you've seen one of those before. So these things, or if you have one of those portable heaters in your house that has that big like silver sort of dish and has that stuff in the middle and you get really hot. You guys ever experienced any of those things? Those are all examples of one kind of radiation, and the sun emits a whole lot of it, and we feel that. Yeah, so some of you experienced that before. That's the infrared radiation. So if we're looking at the electromagnetic spectrum, infrared is right here. And then we get into visible light, which is kind of the breaking point where energy that the waves possess starts to get dangerous, just past visible light. If you sit outside on a sunny day, you feel warm. That's nice. Just baking in the sun. But what happens to your skin if you sit outside in the sun too long? And what type of radiation causes sunburns? It's not the infrared. You guys are probably familiar with the type of radiation that gives you a burn. This is kind of one of these spots where it's like, fairly obvious that, okay, I can feel warmth from the sun, and then you get a sunburn. That's as a result of what type of radiation? There's a couple of you typing. UV, yeah, so UV is ultraviolet. If you think of a rainbow, red is at one end and violet is at the other. If you look at the electromagnetic spectrum, I forgot to mention that. Thank you for reminding me, Taylor. The learning guides, for whatever reason, I didn't create them. The learning guide for Unit 7 is slightly different than the previous learning guides. I'm not sure what it was. I was going to redo it, and then I'm like, well, it kind of flows. So instead of having just blanks for you to locate the vocabulary terms and things in, it just asks questions. So the first question is something like, where does radiation exist? And then if you look at the top, it says, radiation consists of high energy and it exists all around us. So it kind of asks questions and then it answers it. So instead of just filling in the blanks, you kind of need to look a little bit harder. So if you're missing something or you're kind of confused, let me know. So UV rays, where is it going? The rainbow. One end you have red, and it goes red, orange, yellow, green, blue, violet. So one end's red, that's the infrared, is right next to red. And then the other end's violet, and then ultraviolet. So infra just means below red, and ultra means above violet. So that's where we come up with the names. Of those things, Alex, I saw a video on YouTube where this guy held a piece of glass, the sun, showed the colors of the light, then used a spectrometer, I believe you're writing, to compare different types of light bulbs to the sun. Really interesting. I think you actually do that in grade 9, maybe 8. Grade 8 use light spectrometers, and we can do really cool things with spectrometers. So what you're talking about is different elements produce different wavelengths of light. So if you have ever seen like a neon sign, depending on what type of gas they put in it, if they put neon in it, makes one color, put argon gas, another color, krypton gas, another color. Depending on the color or the gas, when you get it excited, it produces different colors. And that's how we know what some stars are made of. We can hold a spectrometer up to a star. If it has lots of like red wavelengths, then it's probably made a lot of like hydrogen. And then if the star's moving towards us or away from us, it gets blue shifted or red shifted, called the Doppler effect. And we can tell how fast the star is moving by how much the spectrum has moved. So yeah, that's a really great example of using the electromagnetic spectrum. There's tons of stuff you can do with it. So here's kind of the spectrum broken down a little bit further. We talked about visible light being in this one little itty bitty section here, and then we had infrareds on one side and ultraviolets on the other. And everything on this side of visible light, so visible and up, is dangerous to us. It's called ionizing radiation. It can hurt the DNA in our bodies. We'll look at that in a second. Everything below is kind of lower energy, and everything down here passes through your body pretty consistently, and you don't really have any negative effects as a result. Right now, if I had a radio in this room, I could turn it on and there'd be radio waves in the room. Microwaves, very common. The sun's giving off all sorts of these things all the time. We've harnessed some of these waves. So AM waves, AM radio, we don't use it very often, but you can. That's 10 to the 3, so 10 times 10 times 10 is 1,000. So the wavelength, the physical length of these radio waves is about 1 kilometer long. and then we get a little bit shorter. FM waves are about the length of your house. Microwaves are about 1 meter long, and then radar is a little higher. And then you get even smaller into sort of unfathomably small stuff. So that's how big these waves are. So that's the electromagnetic spectrum kind of broken down into its parts. As you can tell, most of this stuff's invisible. We can't see the radio waves moving through the room right now, but they are. There's radio waves in the room. There's microwaves in this room right now. I can't see them. Our eyes are very tuned into one specific part of the electromagnetic spectrum, and that's the visible portion of the spectrum. You'll hear some about animals that can see different parts of the spectrum. So some animals can see a little bit into the UV and a little bit into the IR. And you can imagine, or you've probably seen it before, like night vision goggles. How do those work? There's a couple different ways they can work, but they take stuff out of the infrared part of the spectrum, which is just below visible light. So anything that has, anything that exists exhibits a certain amount of heat. And if you can convert the amount of heat something's producing and you shift it based on the more heat, the more color, you shift it into the visible part of the spectrum, we can create sort of night vision stuff based on moving a part of the spectrum we can't see into a part that we can. So all these rays and waves are invisible. And there was a guy named Röntgen, and he discovered X-rays. So he's like, I have no idea what these are. I'll just call them X for now. Just kind of like in math, we don't know a variable, we call it variable X. I don't know the height of a tower. I say, okay, let that be X. Just an unknown. And he called them X-rays, and the name just stuck. He never intended to call them, like he wanted to name them, or once he got more information to figure out what they actually were, he found a whole new type of ray, and he called them X. And now 150 years later, we still call them X-rays. So that's kind of interesting. Henry Becquerel realized uranium emitted invisible energy as well, which was kind of interesting. And Marie Curie and her husband Pierre, they did a lot of research into radioactivity. Interesting story about Marie and Pierre. So they were pioneers in discovering things to do with radiation and radioactivity. And at the time, this is, almost 100 years-ish ago, females weren't really respected as scientists. Females were to be in the home, produce children, cook, clean. That was just the traditional gender roles in kind of European, North American cultures. And she was really, really smart. She was way smarter than her husband, Pierre. But a lot of the sort of stuff that she did because she was a woman didn't get recognized. So it wasn't until many years later that people started going back and looking at their notebooks and things and starting to see that a lot of the notes were written in her writing, not his. Most of the discoveries were created by her, although he kind of supported her and they were both really bright. But she was the one who, deserved most of the credit but didn't unfortunately get it until years later. Turns out they both died of radiation sickness because they played with all this stuff so long. They didn't realize it was harmful at the time. And that's how they both passed away, just because they played with radiation too much. So this was actually the first discovery of radiation right here. This is an image of it. So back 100 years ago, if you wanted to take a picture, you'd have those big cameras and you'd slide a plate in it. And then once the plate was in it, you'd sit there and they'd open the shutter and the light would come in. And then you'd have to stay really still for, about a minute or so. And then they'd close the shutter, block all the light off, and then they'd go develop the plates. So what had happened is in this laboratory, they'd had a rock and they set it down on this photographic plate. They went to develop the picture later and they found this sort of pattern on it. And they're like, I wonder what caused that. Obviously, it wasn't the picture they were trying to take. So they discovered that the rock that they had sat down on top of this photographic plate had developed the film, the actual film part of the photographic plate. So they said, there's something going on here. Some invisible thing is happening between that rock and the plate. and this is how sort of radiation was discovered. We've obviously come a long ways since then, but we have more accurate ways of discussing or discovering or measuring this sort of stuff now. So if we take a step back to just before spring break, we started looking at the periodic table. And I forget who it was, someone asked, well, how come, Mr. Borden, the mass numbers on the periodic table are decimals? And I said, just round them up. We're going to get to that later. Does anybody remember who asked that question, or was it you? Speak up. I want to recognize you for your great question. Once again, we've moved forward, and now here we are. We're going to talk about why those mass numbers are rounded. So the idea is this. There's something called isotopes, and not all elements have them. Some do, some don't. And the elements have the same number of protons, because if we change the number of protons, it becomes a new element. So we're talking about one type of element, one number of protons, but the number of neutrons changes. It gets bigger or smaller. And as soon as you change the number of neutrons, the mass changes. But it's still the same element. If you are hydrogen, you have one proton. If you're hydrogen and you get a neutron, you're still hydrogen, but you have a neutron now. If I give you another neutron, you're still hydrogen, you have another neutron. So as soon as we talk about adding neutrons, we get different isotopes of elements. They weigh different amounts. So the example here, you won't be expected to calculate this until grade 11 if you take chemistry, but in nature, there's boron all around us. About 20% of boron atoms have 5 neutrons. About 80% have 6 neutrons. So if you can imagine, we take 19%, or 0.19 times 10, and 0.8 times 11, we add it together, we end up with 10.8, which is the atomic mass of boron. That's how we get the decimals. We're ending up kind of taking, okay, there's a bunch of this in nature, there's a bunch of this, but there's more of this. So we need to kind of, recognize that boron usually weighs this much, but sometimes weighs this much. So here's a couple different examples of isotopes, and carbon's a really important one, and so is hydrogen, but carbon's important because all living things contain carbon. So you can see the different isotopes of carbon. Carbon always has 6 protons, so the green dots here are the protons, 1, 2, 3, 4, 5, 6. There's 6, 6, and 6. Each one of these examples has 6 protons. But I can have different carbon. I can have carbon 12, which is carbon with a mass of 12. That's 6 protons, 6 neutrons, stated down here. If I add an extra neutron, an extra one of these kind of orange balls, I get carbon 13. It still has 6 protons, it's still carbon, but I've added an extra neutron. If I add another neutron, I end up with another one of these kind of orange balls. So I have 6 protons, 8 neutrons, 6 plus 8 is 14. That's carbon 14. So this is kind of the notation you're going to see. An element with the mass number next to it. Because as soon as you have the element name, that's how many protons it has. And then the mass number comes after. You can see below you have the isotopes of hydrogen. They're common enough that we give them names. Protium, deuterium, and tritium. And if you're a big Spider-Man fan, I remember teaching this during, I forget which Spider-Man movie it is, but I think it's the Doc Octopus one, if anybody knows which one that is. They're harnessing tritium. They're using it to make his suit or something. I forget what it is. Somebody's a Spider-Man fan. They chime in here. So they were looking at tritium, which is an actual isotope. So for the rest of this kind of unit, you're going to see elements like this above my head. The big X is going to be the element symbol. So carbon, hydrogen, potassium, whatever. On the top, this is going to be the mass number, so how much it weighs, which is your protons, neutrons together. And then on the bottom, you're going to have the number of protons. So it's just kind of shorthand for writing different isotopes. So it's going to be really common. We're going to use it all the time. So let's look at a couple examples. Potassium is a very common element. It's found in bananas. So if you had a banana in your house, it has a bunch of potassium in it. Now, some of the potassium in your banana is going to be potassium 39. Some of the banana is going to have potassium 40, and some of it's going to have potassium 41. That's just a natural breakdown of the 3 stable isotopes of potassium. So you can see the notation we're going to use here. K is potassium. It has 19 protons. That never changes. If I added another, it's no longer potassium, but the mass can change by altering the number of neutrons. So again, potassium 39 has 19 protons, potassium 40 has 19 protons, potassium 41, 19 protons. If I add a neutron, I get potassium 40. If I add another neutron, potassium 41. The electrons also stay the same. So just kind of get to the potassium on the periodic table. If I look on a periodic table, potassium has a mass of 39.1. Where does that come from? There's 3 isotopes of potassium. Well, it turns out that almost all of the potassium in your banana is potassium 39. And the actual breakdown is 93% of the potassium has a mass of 39. About 1% is potassium 40, and about 7% is potassium 41. So if you break down all those percentages by the masses, you end up with 39.1. Majority is the 39, but the rest kind of adds up the mass a little bit. So that's where the atomic masses on the periodic table actually come from. Averages of the isotopes. You'll notice some of them are whole numbers with no decimals. That just means that they don't have any stable isotopes. Not all elements have stable isotopes. So if they have a decimal, that means that there's some isotope that's stable. No decimal, it's likely that just exists as it is. Does anybody have any questions thus far about isotopes? We're going to look at some examples using these coming up, but we're good. We got it under control. We're clear. Clear as mud. Excellent. All right. The next thing we need to look at is radioactive decay. Thank you, Ava. So when we looked at balancing chemical equations, I said we use the law of conservation of mass. We said matter cannot be created or destroyed by ordinary chemical means. And before that ordinary chemical means part was kind of added in there, for a really long time, people said atoms are there, they can't be created or destroyed, that's it. But we discovered radiation about 100 years ago. And it happens that atoms can be created or destroyed. And we can make elements from other things. So like uranium will break down eventually into lead. It's just how it decays. It'll break down because it's radioactive. So when we talk about things being radioactive, typically we'll have something like, I don't know, like carbon. Carbon isn't really radioactive. Why? It's very stable. The nucleus is really small and it just exists that way and it's kind of happy. Once you get really, really big nuclei, so we're talking things bigger than like 92 protons, we're talking atomic masses close to 200. Once you get really big, things get unstable. And they want to break apart to become more stable. Small is stable, big, unstable. So really big elements break down radioactively. They have too much energy in the nucleus, and there's not enough force holding them together, and they'll break apart. And that's what we call radioactive decay. And we'll spend a bunch of time looking at it quite closely. So things will keep breaking down until they become stable. And only certain things are radioactive. Not everything's radioactive. Only certain elements are. So we're going to talk about the 3 main types of radiation and what's kind of makes them special. And then we'll do some examples with them. So there's a guy named Rutherford, and he identified the 3 different types of radiation, alpha, beta, and gamma. A, B, and C, or alpha, beta, gamma, are 3 letters from the Greek alphabet. It's kind of like the letters of our alphabet, but they're Greek letters. So you can see they have fancy symbols. This fancy little A here, This is what the Greek letter alpha. This fancy B is the Greek letter beta. And this fancy Y is the Greek letter gamma. So these are your 3 types of radiation. Now, we haven't looked at them yet, but this picture is super important, and there's always questions that come up in regards to this, so maybe it'd be worth looking at later once you have a better understanding of these things. But this is kind of how old TVs work. So if you have a cathode ray tube TV, this is how they work. You get some sort of source producing energy, and then it goes through here, and then they bend the waves with plates. So alpha particles have a positive charge, so they will be repelled from the positive plate and be attracted to the negative plate, so that's why they will curve down. Beta particles have a negative charge, they'll curve up because they're attracted to the positive, repelled from the negative, and gamma just continues on right through. They're not charged, so they don't experience any effects when you get sent through a field that's created here. So these are your 3 particles, and we'll look at them all in depth. Alpha radiation, alpha particle. So alpha radiation is a stream of alpha particles, and alpha particles are just a helium nucleus, which is kind of weird. But it just so happens that in nature, lots of elements that are radioactive get rid of alpha particles. They emit alpha particles, and alpha particles are just 2 protons and 2 neutrons that kind of stick together. They have no electrons buzzing around the outside. It's not helium, but it's just 2 protons, 2 neutrons. So it has a charge of +2 because it has those 2 positive protons, and then the 2 neutrons are there, which just have no charge. And the alpha particles are easily blocked by a piece of paper, your clothing. Even if you were to sit next to something producing alpha particles, you have enough sort of dead skin on the outer layer of your skin that could stop alpha particles from penetrating your tissue and making you ill. So that being said, how is it possible that we're ever concerned about alpha particles? How can alpha particles make us sick? How can they harm us if our skin can block them? Can anyone think of a way that an alpha particle would make you, could injure you or damage you even though your skin can stop it? Can't get through your skin, piece of paper, clothing stops it. How could it get sick? A wound is possible, but if you had a wound big enough to absorb a bunch of radiation, you'd probably be worse off because of the wound. Any other ways we could get sick by alpha radiation? Somebody got their thinking cap on today? Come on. What if, Ava's gonna try. Okay, what if the alpha radiation wasn't on the outside of you? How could you conceivably get alpha radiation inside of you? So ingesting it, that's a big one, Anna. Yes. Another way? So alpha radiation can be in food that you eat. So imagine you're in a radioactive area, a plant grows in the radioactive soil, it absorbs all the radioactive material, you eat the fruit, now the radiation's inside of you, you get sick. Mouth and ears, yeah, so Ava, that's exactly right. What are common ways it can get into your body? If you inhale it, so there's radioactive dust in the air, you inhale it, now it's in your lungs. Gets trapped in there, produces radiation constantly. Alpha particles damage your cells in your lungs. If you were to ingest it, those are both really common ways of getting sick as a result of alpha radiation. So great work. Now, we haven't done any of these examples, but we will here look at them in a second. This is radon, or radium I should say, and it breaks down into radon, and basically it's really big and it's really unstable. So radium with a mass of 226, it is unstable. So how does it become stable? Well, it needs to get rid of some energy. So it goes bloop, and it breaks apart into 2 things. It breaks apart into radon, and it breaks apart into an alpha particle. So if you have one atom of radium, it can be unstable. To become stable, it gets rid of an alpha particle, which actually changes. We call it transmutation. It changes into a whole nother element. Radium breaks down into radon. And it turns out that this is a process that doesn't just stop at radon, it continues to go. So one really cool thing about this is kind of why it's in the chemistry unit, is all the math works out. If you're radium and you have 88 protons, and you're sitting there, you have 88 protons, and all of a sudden you lose 2 protons and 2 neutrons. Well, now you don't have 88 protons anymore. You've lost 2, so you're now down to 86. If you have 86 protons, you're not radon or radium anymore. You're now radon. You've become a new element. So we can look at the math and figure out, well, if it loses an alpha particle, it's going to lose 2 protons. It's going to go from radium to radon. These words are too similar. This is a cloud chamber here on the left. Basically, it's just a chamber that has some really cool characteristics, different pressures and temperatures and things like that. But what is happening here is you can see that there is a little puff here, and all of a sudden a bunch of radon gas is released into this cloud chamber. And you can see those little streaks that get created. Those are all alpha particles being emitted by that radon gas. So the radon is decaying and it's giving off these alpha particles. And because they have so much energy when they go through this kind of cloud chamber situation here, they release these alpha particles. And you can see the little streaks that are left behind. So how do we get radon gas? Well, it turns out that uranium likes to break down to become stable into radon. And then radon gives off an alpha particle, becomes polonium, which breaks down to lead, which breaks down to bismuth, polonium, and then back to lead again. So uranium does these steps, and we'll talk about this more later, but it's this 1, 2, 3, 4, 5, 6-step process to change from uranium to lead, where it's stable. Why do I even bring this up? Why do you care? Has anyone heard of or had their house tested for radon gas before? It's pretty common. It's fairly common in the Okanagan because where we live, a lot of houses are built on kind of rock structures, and sometimes the rock has a little bit of uranium in it. We're not talking like a lot, but just a little. Don't think so? All right. Basically what happens in areas where houses are prone to radon gas is they'll build the house and there'll be rock where it's built into, or the concrete that they mixed for the house has a little bit of uranium. Like, I'm talking very, very minor amounts. But what can happen is the uranium that's in this stuff can break down into radon gas. And that radon gas can actually build up in basements of homes or places where there's very low ventilation. So the radon gas doesn't get blown out. It just kind of builds up, and builds up. Now all of a sudden you live in the basement of this house and you're breathing the air in, and you can't taste it or anything. It's odorless, invisible gas, but you're inhaling small amounts of radon gas all the time. And that radon gas is giving off these alpha particles, which again, you can't see, and you can get sick. You can get increased risk of developing things like lung cancer because of radon gas in your house. And it's common for people to have their house tested or the area around your house tested for radon gas, especially in specific areas, especially with homes built into rocks. So these are kind of examples of some of the equations we're going to work with, and I'm just going to jump over to the learning guide in a second, and we'll look at a couple examples there. So we did this radium to radon example already, and there's two different ways we can represent this alpha particle. We can write it with the Greek letter alpha and write a 4 and a 2, or we can write it as He, like a helium nucleus, and write it as a 4 or 2. So either one of these things is completely acceptable. They both mean the exact same thing. They are one and the same. So you can write the fancy alpha if you like, or you can write 42HE, and you have to be able to recognize kind of both of those. So if we jump over to the Unit 7 Learning Guide, we did carbon. I thought there was some specific examples, but they are broken into one table. So what we're going to do is we'll look at beta and gamma, and then we'll come back and we'll look at some of the examples here. All right, so that's alpha. Beta radiation, another Greek letter, fancy looking B. Beta radiation is a really high-speed electron. And it's usually at about this point where some astute student says, Mr. Borden, in class, they usually raise their hand. You guys just write stuff in chat. But a student usually says something like, Mr. Borden, where did the electrons live in an atom? And then I say to them, well, they fly around the outside. They fly around the nucleus. And then they're like, okay, that's what I thought. Mr. Borden, why is there an electron coming from the nucleus of an unstable atom? And that's a really legitimate question. How the heck did an electron get into the nucleus of an atom? We spent all this time talking about Bohr models and Lewis diagrams. We have this nucleus, and you have all these electrons flying around the outside in these clouds. So how does that nucleus have electrons in it? Really weird stuff happening here. And it is really weird. What actually happens is a neutron in the nucleus, it actually breaks apart. So one neutron will split into two things. And it turns out that neutrons are made up of protons and electrons stuck together. So if you're a neutron and you all of a sudden become unstable, too much energy, boom, you can split apart into a proton and an electron. Now the electron will go whiz flying out of the nucleus and it gets emitted as radiation, but the proton stays on the inside, which is kind of interesting. So if you have iodine, we talked a little bit about the iodine radiation from Fukushima that was in the atmosphere. Iodine-131 is an isotope of iodine. If iodine becomes unstable, and this isotope is unstable, and it gets rid of a high-speed electron out of the nucleus, so a neutron actually changes into a proton and electron, it's no longer iodine. The atomic mass was 131. It stays as 131, but the number of protons changes. It changes from 53 to 54 because one of the neutrons actually changed into a proton. So we're no longer element 53, we're now element 54. Really kind of a complicated sort of idea to wrap your head around. The atomic mass doesn't change. A neutron changes into a proton. When we talk about atomic mass, it's the protons and neutrons added together. So we're not gaining or losing atomic mass, but we're gaining a proton, which kind of sounds like we're gaining atomic mass, but it's changing from a neutron. And that new proton alters the atomic number. And if we've altered the atomic number, new element. That's beta radiation. Couple ways we can write beta radiation. We can write it with a fancy B, a beta, or we can write it as an electron with an E. And because this is an electron, electrons have a charge of -1, we write down 0, -1 with the B. So that is what beta radiation can look like. And the math works out. You start with 131 equals 131 plus 0. Yep. 53 equals 54 minus 1. Is that true? Yes. 54 minus 1 is 53. So we're going to look at some examples of these types of questions. Beta. Any questions on beta or alpha? Nope. All right. The last type, oh, my little gamma didn't load properly. That's okay. The last type of radiation is gamma. And gamma is, these are like the gifts that you get. You know how I talked about like, oh, when you're doing compounds, you get a covalent compound. Those are so easy, they're gifts. Gamma radiation is a gift because it's just energy. Something's really unstable, and then it just wants to get rid of some energy. So boom, gives off a little bit of energy. That's it. And when you do these types of questions, you can see the examples down beside me here. It's kind of easy to recognize them because they always have this star. And this star is like telling you that these things are unstable. So it's not giving off any mass. It's nickel to begin with, it's nickel to end with, or it's a little bit more complex process down below here. But it starts as nickel, it ends as nickel. Started with 60, ended with 60. Started with 28, ended with 28. And it just gives off a gamma particle or gamma wave. Just a little packet of energy. Zero mass, just energy. So something becomes unstable, gives off some energy, and boom, you end up with gamma radiation. Now, we talked about alpha radiation being able to be stopped by things like clothing. Beta radiation has a little bit more penetrating power. Maybe something like aluminum foil can stop beta. Gamma can penetrate through your body, makes you really sick, and it can go through several inches or centimeters of concrete. So to stop gamma radiation, you usually need a couple centimeters of something really, really dense like lead. Lead metal is really dense. So we'll look at the summary, and then we will go look at a few of those examples for you, Ava, and everyone else. So we're going to do these just like we did chemical equations, which is really cool because you're really good at those, and a little bit more of the same sort of stuff. Alpha radiation, it's alpha particle 4, 2, beta is 0, -1, and gamma is 0, 0. Wouldn't it be really great if you could find these somewhere? If, say, they were given to you, where do you think you would find these? Somebody go find the page that it's on the really important thing that you have for Science 10. Go look, it's there somewhere. Anyone have it sitting next to them? Anyone? Yes? No? It's in your data booklet. So you don't have to memorize the symbols. It's all there for you. All you need to know is the difference, which symbol represents an alpha, which symbol represents a beta, and which symbol represents a gamma, which is pretty straightforward because the alpha kind of looks like the letter A, the beta kind of looks like a B, and if you're confused about gamma because it's a Y, then fair enough. But if you can figure out A and B, then the last one has to be gamma. It is at the end, it's on page 12, it's the very last page of your data booklet. There's a little chart in the middle of the page that has alpha, beta, gamma. It has it as an electron for beta and the B. It has the alpha particle and the He, and then it has the gamma. So it's all there given to you, which is kind of cool. It doesn't tell you much more than the symbols, but they are there. So less for you to remember. Alpha particles have a charge of +2 because there's 2 protons there. Beta is -1, gamma is 0. Alpha particles can be blocked by paper. Beta can be stopped by something like tinfoil, and then something like gamma has to be blocked by lead. So there you go. That's a little summary of those 3 types of radiation, alpha, beta, gamma. It's kind of what we're going to talk about today. Let's look at some examples, and then we will come back. I have a few things I want to show you, but that's kind of it for today, I believe. So this is your learning guide. This is on page 3, down at the bottom of the page. Now, these are decay equations that are kind of partially filled out, and you need to kind of do a little bit of math and some thinking to figure out what we're going to end up with. So the first example here, we have PO, and it doesn't even really matter what this is. I think it's either polonium. I think it's polonium, yeah. And remember, when we have an equation, the arrow is kind of like an equal sign in math, and that's how we're going to treat it. And what we're going to do with these types of questions is we're going to take all of the things on the top and make an equation with them, and all of the things on the bottom and make another equation with them. And each side of this arrow has to be equal. So one side has to be equal to the other. So I'll show you what I mean by that. So let's say I'm polonium. I'm unstable, I give off a beta particle, and you're interested in figuring out what's left. Okay, if we look at the top numbers here, if we think of this as a math equation, it looks like this. 216 equals 0 plus what? If we started with 216 and we ended with 0, what do we have left there? Seems like a pretty straightforward type of math question, and none of these will get terribly difficult. We end up with 216. So you can imagine writing 216 in there. Perfect. On the bottom, a little bit trickier. We're going to do this equation now. So it's going to look like this. 84 is equal to minus 1 plus something. 84 equals minus 1 plus something. You would be surprised to find out how often students make an error on this. I don't think it's because they don't know how to add -1 to things. I think it's because students tend to rush through things. And if you're rushing through things, you kind of get caught up in it. So yeah, 85. Great, Anna. So if I put an 85 down here, and I put in here, 85 minus 1, or plus -1, is 84. That's perfectly right. So I'm going to erase all this. You don't have to, but it's just going to make this look a little bit nicer. All right, I'm interested in figuring out what element is here. Which of the two numbers am I going to look to figure out which element I have? Am I going to look to the bottom, the 85, or am I going to look to the top, the 216? I'm going to break out my periodic table. Top or bottom, 216 or 85? Am I looking for element 85, or am I looking for element with a mass of 216? Element 85, I like it. Remember what that 85 represents. This is the number of protons, which is the element you're dealing with. Perfect, thanks guys, you got it all right. So remember now we're dealing with isotopes. These are kind of different than the things in the periodic table. If you look on the periodic table for something that has a mass of 216, like the mass number at the top, I just quickly glanced through and I couldn't find anything with a mass of 216. So that won't work. So don't look to the top. We don't want to look to the top. We look to the bottom. What is element 85? Hopefully somebody has a periodic table out there. Element 85 to me looks like astatine, which is AT. And then the last part of the question asks us to identify what type of decay this is. So I would say that this is beta decay. All right, why don't you guys try the next one down here, and we'll see how we do. The missing elements at the beginning here, it's just kind of the way it was written down. It doesn't matter, of course, which one gets added first. So try to figure out what element is in there by doing the math again. Think about it in terms of really basic math equations. You started with 234, you ended with 230. On the bottom, you started with 91, you ended with 89. Maybe somebody, once you've figured it out, could put in the element symbol into chat to figure out what this Pa, palladium maybe, what it broke down into. 91. I'm going to look, see if I can find it. I was way off. PA is protactinum. Ava has helium in there, He. Does anyone agree or disagree with He? You could disagree on technical grounds, I suppose. There is another way to answer that. Does anyone know the other way we could answer it? Yeah, perfect. We could write it as alpha as well. So for those of you who are kind of sitting here scratching your heads like, this is kind of weird. We have the math equation here. And on the top we have 234, and then we ended with 230. So if you think about it like this, 234 equals something plus 230. So think about that. I'm like, okay, that's a 4. So I put a 4 up here. And on the bottom, I'm going to do the same thing. 91 equals something plus 89. Well, that's going to be a 2. So I put a 2 down here. And if you're just kind of quick to jump to the periodic table, you'd see 4,2. Oh, that's going to be a helium nucleus. So you could put in He if you wanted, which is great. Or if you're like, oh, that's an alpha particle. 4,2 is a helium nucleus. You could write in your little alpha particle. My alpha usually ends up looking more like a badly drawn fish than it does an alpha, but generally speaking, students get the idea. Maybe I'll take my time here. There's my alpha. I'll do the third one here and then we'll look at a couple things and we'll call her a day. I want to apologize for talking so much today, but just kind of wanted to get all this stuff in an hour. So the next one here is Mg, and as soon as you see the star, a little light bulb should go off in your head. Star, what does that mean? Oh my gosh, what's going on? The star means that this thing has too much energy. So it's going to release some energy to become stable. It's telling you that it's unstable. Now, this is a bit of a typo over here. That shouldn't have a star on the product side, but not the end of the world. If I started with 24 and I ended with 24, well, that changed by 0. I started with 12, I ended with 12. That changed by 0. So I have 0, 0, which is a gamma ray. So just some energy given off there. I'll leave that last one for you to do. I'm confident you guys can do that. I'm just going to scroll down a little bit. Half-life we haven't done. Decay curves, that'll be next day. So you should be able to finish this learning guide up to the end of the 3rd page. I know most of you are probably getting Unit 5 out of the way, so when you get to it, we won't meet again until next week. I'm just going to jump back to the lesson here. Just want to talk a little bit about a couple things, and then we'll call her a day. A lot of people